Okay, welcome back. We are in the second section. This is for honors only. So if you are not in the honors college prep, you can skip this video unless you just want to learn something, which is always a wonderful change of pace. But otherwise, we are talking about some honors reference tables. So we're going to be on honors reference table L when we talk about things in this section. So when we talk about how strong an acid or how strong a base is, there are many ways we can talk about that. One of those ways is pH, but that's not what this is about. This is about how well these things ionize, how well these things give off H plus protons or OH minus hydroxide, how well it creates these ions in solutions. Super strong acids and bases have a lot of ions. They completely ionize. And those are because they are completely ionized, they are good conductors of electricity. Remember, electricity needs mobile ions. Mobile ions. That's an N. Whereas weak acids and weak bases aren't going to ionize completely, just slightly. So if you were to put something into water, stir it up, because remember, these acids and bases are only going to be conductors in aqueous state. So when you put these pellets of something into water and stir it up, there's not going to be as many ions that are able to break apart, and thus they are less conductive in electricity. So how can we tell who's a good conductor of electricity and who's not, aside from making solutions and putting in a conductivity meter or something? Well, we have honors table L, so you should be there pretty shortly. And what we measure is something called Ka. K is a constant, subscript A meaning acid. So this is kind of touching on something that's definitely going to be in Supachem, AP Chem, not as much on the regents, but it's a constant for a reaction that produces those ions. And these are weak electrolytes. So for example, this is acetic acid. How did I know it's acetic acid? Couple ways. First, I could go to regular old reference table K, and that shares its name. The other is, well, I've got acetate right here, and if it leads with H plus and it's aqueous, it's most likely an acid. So acetic acid or vinegar, common name. So vinegar, when you put it into water, is going to break apart. It's going to give you H plus, of course, and it's going to give you the acetate. Remember, this stays together, polyatomic. So if you were to look on honors reference table L, it'll give you a value. I would not worry about any of this math. So this will not be tested. This is just kind of like, so if you see it in the future, you're like, oh, okay, I think I've seen that. So what happens is you do the concentrations. These brackets mean concentration. Concentrations of the products over the concentration of reactants. And of course, these would have to be given to you, and then you would come up with an answer. So this has no unit, it's just a value, and you can see that it's pretty darn small. So 1.8 times 10 to the minus 5. So again, so here's our 1.8, so we move it 1. I actually move it for you. 1, 2, 3, 4, 5. Put the decimal place. So that's 1, 2, 3, 4 zeros, 1, 8. Super duper small. So that's really not going to be giving you a lot of acid particles. So again, sorry that little bar is in the way. If you have a small Ka value like this, means that you don't have as many ions and you have more molecules. And that should make sense because this is a molecule here. This is covalently bonded. It's not going to break apart any further. It's going to stay kind of a chunk in there. The larger Ka values means you have fewer molecules and more ions. So the more ions, the larger the Ka. Is there a unit for Ka? No. And if you look on table L, which I'll get there here, you just see that some of them are just very large. There's not even a number given. Then you just have large. Then you have quantitative values all the way to the super duper small, and then it's just very small. So, man, I really wish I could show you down here, but this little picture box is here. It says that H plus aqueous, so protons that are dissolved in water, are equivalent to H3O plus. You remember what that's called? It's called hydronium. If you did not remember what that's called, it's on reference table E, the regular one. And then that shows it shows Bronsted-Lowry acid and base pairs. These are Bronsted-Lowry base pairs. Do you remember what a Bronsted-Lowry acid-base pair is? If not, you should probably go back and look at the last video, but I'll tell you anyways. So it shows somebody donating protons, that's the acid, and somebody receiving the protons, that's the base, under the definition of Bronsted-Lowry, which is different than Arrhenius, so that's why they call it the alternate theory. I'm getting ahead of myself, so let's go back. So we're still using that reference table L in the honors section. In Bronsted-Lowry theory, strong acids will easily lose their protons. Their conjugate base will be weak. The acid dissociation constant is larger for strong acid, weak base conjugate pairs. Okay, let's break that down for a second. Just let it sink in. So the larger the Ka, the stronger the acid, the weaker the base. Okay, because there's more ions if you have a larger Ka. How do I measure Ka? Who cares? It's just a value for this point. You will get much deeper into that into the higher level chemistry. So back to reference table L. Again, we're using Bronsted-Lowry theory. So notice we have Hi as the acid. So H is going to donate its H to iodine. So here's our base. Look at this. This is just a whole H plus. So here are our acids. Here are the base, and that's under Bronsted-Lowry theory. So Ka, this would be the strongest acid, hydrogen iodide. I don't believe we have it in our chemical storeroom in a high school, possibly in a college lab or a pharmaceutical or, business lab. And so you go down, these are going to be weaker. So this is a strong acid, strongest, to the weakest acid. And looky here, who's here at the bottom? Ammonia. Wouldn't it make sense that ammonia is a weak acid? Because whoop, it's not an acid. Ammonia is a base. So strong acids to the weakest acids. These are the weakest base. And you can barely read that, I apologize. Weak base going to the strongest base up here. So this is, I don't even know that off the top of my head. That's stronger than hydroxide. So as far as how I'm going to be testing you, basically it's going to say who's a stronger acid. And if you have no other way to tell, try honors reference table L. Isn't that right? Okay, so here are two terms that you should be familiar with, Amphoteric and Amphiprotic. Stupid mouse. I generally use this term, Amphoteric. I don't know why. They are synonyms. You can use either one. But what it means to be amphoteric is you can be a Bronsted-Lowry acid or a Bronsted-Lowry base. So it's a substance that can either give away H plus or accept H plus. So if we're using that honors reference table L, they would be found on either side. So here's an example. So let's assign conjugate acid-base pairs using Bronsted-Lowry theory. So we have H3O plus here. Who looks sort of similar to that on the right side? H2O. Okay, so to go from H3O plus to H2O, looks like I've lost a proton. So this must make this a Bronsted-Lowry acid. HSO4 minus becomes H2SO4. Gee, looks like I gained a proton. So this must be the base. H2SO4 becoming this must have lost. H2O becoming that must have gained. So let's assign our conjugate pairs. Acid base, acid base. Thanks a lot, Screencastify. So again here, are you kidding me? HSO4 minus to SO4 2 minus, looks like I've lost an H, so that's an acid. OH minus to H2O, that must have gained. Going in the reverse, that makes this an acid. Going in the reverse, that makes this a base. If I did that too quickly, please go back to the earlier and take a look at how to assign those. acid and base, acid and base. Now, if you look here, HSO4 minus is acting as a bronzolari base. Over here, HSO4 minus is acting as a bronzolari acid. Because it can do both, that makes it amphoteric. Let's go back here. Let's look for amphoterism. So who is found on this side, acid, as well as this side? Let's see. Put me on the spot here. OH minus. There's one. Let's see. I'm sure you're finding all of them and making me look like a blind old bat. There are more. Water is also one. Water, you can include water. There's more. Gosh darn it. I should have prepped. SO4 sulfate, I believe. No, well, there's more than that. I trust you. Just go ahead and find them if you'd like. Amphoteric means they can act as either bronzolari acid or a base. And the last thing I want to talk about is something called Kw. K meaning another constant, W standing for water. So water, sitting in your glass, sitting in a water bottle, is constantly going to be self-ionizing, meaning H2O breaking up into H plus and OH minus. But it can also grab a proton just floating around and become hydronium. So all of this is happening. So Kw is equal to the concentration. Those brackets means concentration. And I know it's really hard right now because I'm not putting any numbers in there. We will later. So the concentration of your acid particles times your concentration of your base particles is going to give you a value of 1 times 10 to the minus 14. Again, no actual units. It's just a value. If water is neutral, which you know from other science classes it should be, then the concentration of the acid must be the same as the concentration of the base. And since they're the same and they have to equal negative 14, then they're both going to equal 10 to the minus 7. And 7, isn't that a number that kind of relates to neutral? It should. The pH of neutral substances is 7. So the way we got that has to do with this. But again, this is honors only. This will not be found on the Regents, and probably not too much on a test, but just be aware that since water is neutral, pH-wise, it should have the same amount of the acid particles and the OH minus particles. So that's pretty much all there is to say about that. Thanks for watching.